All right, so in our last explainer, we saw that electric charges have this amazing power to attract and repel each other. But that left us with a pretty big question, right? How do we actually measure that force?
So let's just jump right in. We know there's this push and pull going on, but can we slap a number on it? Can we predict exactly how strong that push or pull is going to be? Well, that's exactly what we're going to figure out today.
You know, to measure anything, doesn't matter if it's your height or the weight of an apple, you need a standard unit. Everyone has to agree on what a meter or a kilogram is. And for electric charge, our standard unit is the Coulomb. It's named after the physicist Charles Augustin de Coulomb. So from here on out, whenever we're talking about an amount of charge, we're talking about coulombs.
Now, let's get some perspective here, because a single Coulomb is actually a huge amount of charge. I mean, look at this number. That's the charge of one single electron. It's an unbelievably tiny fraction. You'd need something like 6 quintillion electrons just to get to one single Coulomb. It's wild.
Okay, so we've got our unit. Now it's time for the main event, the beautiful, elegant formula that brings this all together.
And here it is. This is Coulomb's law. Now I know, it looks a little mathy, maybe a bit intimidating, but stick with me because it's way more straightforward than it looks, and it's incredibly powerful.
So let's just break this thing down. F is the force. That's the number we want to find. Q1 and Q2 are just the amounts of charge on each of our two objects measured in coulombs. R is how far apart they are. And that K, that's just a special number called Coulomb's constant that makes all the units work out perfectly. That's really it.
Now, out of all those pieces, the one you really have to wrap your head around is the distance r. See how it's squared on the bottom of the fraction? That little detail is a huge deal. It creates something we call an inverse square law, and this idea pops up all over physics.
So what does that actually mean for us? It means that distance has a massive effect on this force. If you take two charges and you double the distance between them, the force doesn't just get cut in half. No way. It becomes 4 times weaker. If you triple the distance, it's 9 times weaker. Think about it like a flashlight. The beam gets way, way dimmer the further you move it from the wall. Same principle.
All right, enough theory. Now that we have the rule book, let's actually put it to work. Let's tackle some common questions and really see this law in action.
So let's think about our formula. What do you think happens to the force if we keep the distance the same, but we double the amount of charge on just one of those objects? Yep, the force also doubles. It's what we call a direct relationship. You put more charge in, you get more force out. It's as simple as that. Okay, next question. You might have noticed in the formula that we use the absolute value of the charges, which kind of ignores if they're positive or negative. So if the math only gives us the strength of the force, how do we know if it's a push or a pull? It's actually super intuitive. The signs of the charges tell you the direction. If the signs are the same, 2 positives or 2 negatives, they repel. It's a push. If the signs are opposite, a positive and a negative, they attract. It's a pull. So the formula gives you the how much, and the signs tell you which way. So this is a really neat physics equation and all, but why should you care? I mean, outside of a classroom, what does this formula actually do for us in the real world? Oh man, the answer is just about everything. This isn't just some formula in a textbook, it's the fundamental rule that holds so much of our world together. In chemistry, it explains how atoms bond to make molecules. In electronics, every single circuit in your phone works because of this law. It's even at work in our bodies, shaping the proteins and DNA that make us who we are. And yeah, everyday stuff like static cling, or even the immense power of a lightning bolt. It's all governed by this one, single, beautiful rule.
It really makes you think about what the engineer Charles Proteus Steinmetz said, that studying the electric field is reason enough to study mathematics. And this law is the perfect proof. It's the pure language of math, describing an invisible force that shapes our entire reality.
And that really gets to the magic of physics, doesn't it? We just found one simple, elegant rule that explains this incredibly complex dance between trillions upon trillions of tiny charges. It just makes you wonder, what other simple, unseen rules are out there governing the rest of the cosmos, just waiting for us to find them?